This video will illustrate how to calculate the economic order quantity, or EOQ, along with the reorder point with safety stock and the inventory position under a fixed quantity inventory system, or FQS. We'll also calculate the safety stock under a fixed period inventory system, or FPS. Here's the basic data for our problem. Crew Soccer Shoes Company is considering a change of their current inventory control system for soccer shoes. The following information is provided. The demand is 100 pairs per week. The lead time is 3 weeks. The order cost is $35 per order, and the holding cost is $2 per pair. The cycle service level is 95%, the standard deviation of weekly demand is 50, and the number of weeks per year is 52. There are 3 requirements for this problem. In requirement A, assuming the company decides to use a fixed order quantity system, or FQS, what will be the reorder point and the economic order quantity? For requirement B, in this system, at the beginning of the current week, the materials manager, Luke, checked the inventory level and found 300 pairs. There were no scheduled receipts or back orders, and should he place an order? Requirement C assumes a change to a periodic review system, where inventory is reviewed every 2 weeks, and asks us to determine how much safety stock is required. Let's start with requirement A, and first calculate EOQ because it's the easiest. The formula for EOQ is Q star equals the square root of 2 times D times CO divided by CH, where D is the demand, CO is the order cost, and CH is the holding cost. Q star equals the square root of 2 times 100 pairs per week times 52 weeks per year times the $35 order cost divided by the $2 holding cost. So Q star equals the square root of 364,000 divided by 2, which equals 426.6 or 427 pairs of shoes. We can now move on to calculate the reorder point. The formula for the reorder point is R equals the mean lead time demand, or mu-L, plus Z times the standard deviation, sigma, during the lead time. The mean lead time, mu-L, can be calculated based on D times L, or demand times the lead time. And the safety stock, Z times sigma L, can be calculated using the standard deviation of weekly demand, sigma t, times the square root of the lead time L. Thus, we can rewrite the formula to be R equals D times L plus Z times sigma t times the square root of L. R equals 100 pairs per week times the 3-week lead time plus 1.645, which is the Z value at a service level of 95%, times the standard deviation of weekly demand of 50 times the square root of the 3-week lead time. So reorder point R equals 300 plus 142.46, which is the safety stock, equals 442.5 or 443 pairs. Again, the safety stock is 142.46 or 143 pairs. Therefore, our conclusion is to place a new order for 427 pairs when the inventory position drops to or past the reorder point of 443 pairs. Now on to requirement B, where we need to determine if Luke should place an order. In this part, we're basically asked to determine the inventory position, the formula for which is inventory position IP equals on-hand inventory OH plus scheduled receipts SR minus back orders BO. There are 300 units on hand and no scheduled receipts or back orders. Therefore, IP equals 300 plus 0 minus 0 is 300 pairs. The conclusion here is that yes, Luke should place an order, and the reason why is because the current inventory position does not include the desired safety stock of 142.46 or 143 pairs of shoes. Now on to requirement C, where the company is assumed to use a fixed period system, or FPS. Here we can use the optimal replenishment formula, or the M-level formula, to calculate a little bit more than we need, but definitely the safety stock. Here, M is equal to the average demand per time period, D, times the review period, T plus the lead time L plus Z times the standard deviation during the lead time period plus the lead time, or sigma T plus L. We know all the variables except the last one, the standard deviation, but there's a formula to calculate it, being the standard deviation of weekly demand times the square root of the review time plus the lead time. So we can rewrite the formula to be M equals D times T plus L plus Z times sigma T times the square root of T plus L. M equals 100 pairs per week times the 2-week review period plus the 3-week lead time plus the 1.645 Z value at 95% service level times the standard deviation of 50 times the square root of the 2-week review time plus the 3-week lead time. So M equals 500 plus 183.9 equals 683.9 or 684 pairs. The safety stock here, which is really what we're asked to calculate, is 183.9 or 184 pairs. We can make an observation here that the safety stock under the fixed period system is 184 pairs, which is more in this case, than the required safety stock of 143 pairs under the fixed quantity system. This is due to the fact that the FQS model has to protect against stockouts only over the lead time, L, while the FPS model must protect against stockouts over a longer time period, T plus L. By reducing the lead times and review periods, safety stock can be reduced. We can also note here that it costs $82.80 more to carry the safety stock for the FPS system than the FPQ system. We can confirm that calculation by taking 183.9 under the FPS system minus 142.5 pairs safety stock under the FQS system times a $2 per pair per year holding cost to get $82.80. So basically, to maintain the same service level of 95%, it costs $82.80 more under the fixed period system than the fixed quantity system.